Hello everyone. This is the first of 3 lessons that I'm putting together for you on nuclear energy. So this first one here, just on nuclear reactions, I'll talk about different categories of nuclear reactions. And the other ones, I'll talk about the Canadian nuclear reactor, the CANDU reactor, and then we'll get into some nuclear calculations as well. So we already know a little bit about, of course, nuclear reactions because we've talked about stars, we've talked a little bit about astronomy, and we do know that what goes on in stars is in fact a nuclear reaction. It is a thermonuclear reaction, a fusion reaction that is taking place in our sun and in fact in all of the other stars as well. And that of course is what is generating all of the elements that we do have on Earth and in the universe. So first of all, just to distinguish nuclear reactions, what we're getting into from what we already know about chemical reactions. With chemical reactions, what we're doing is we're taking the reactants, here the methane and the oxygen, we're breaking bonds, we're rearranging the elements, and then we're making some new bonds. So we do have on the product side some different compounds, but we actually have exactly the same elements as what we had on the reactant side. So on the reactant side, we have carbon, we have hydrogen, and we have oxygen. On the product side, we also have carbon and hydrogen and oxygen. Just rearranging the elements to form some different compounds. So this, of course, is a combustion reaction, and we've already done some calculations for combustion reactions. And in this case here, it is an exothermic reaction, and we know that energy is released in the form of heat. And we also know that that energy released in the form of heat from the methane, it can certainly be used for heating, but it can also be used to generate electrical energy. We can also do that with nuclear reactions, not the one that I have below here, at least not right now. So what's the difference between a chemical reaction and a nuclear reaction? Well, now if we take a look at our reactants, we have, and I have simplified this, there are different forms of hydrogen. So I've just written the symbol for hydrogen here. But on the product side, notice that we have something that is completely different. So we're not just making and breaking bonds, we are creating an entirely new element. So we started with hydrogen and now we have helium. So of course this is the primary reaction that is taking place in the sun. This is a nuclear reaction that does involve the nucleus of the elements, and this one in particular is a nuclear fusion reaction. I'll talk a little bit more about that in future slides, but the fusion just means that we're joining together smaller things, hydrogen, and to make something bigger, which is the helium. But the big distinction again between chemical and nuclear reactions is chemical, we're not creating any new elements. Nuclear reactions, we are creating some new elements. So that's everything that I just kind of say in this first bullet point here. The nucleus, remember that that is where we do find the protons and the neutrons. Protons have a positive charge. Neutrons have no charge. Electrons are what we find around the outside. It is the number of protons that determines what the element is. So on the periodic table, atomic number 1 is hydrogen. If it doesn't have an atomic number of 1, it's no longer hydrogen. So that atomic number 1 tells you that there is 1 proton. For helium, the atomic number is 2. It tells you that there are 2 protons. So the atomic number is the number of protons. You cannot change that without changing the element. However, you can change the number of neutrons. So we can have different versions of the same element. So for that hydrogen that I had on the previous slide, what we will see is that they always have to have just 1 single proton, but they can vary in their number of neutrons. So in terms of the number of neutrons that hydrogen can have, it can have 0, 1, 2. Well, at least those are the common ones. There may even be some other ones out there as well that can be synthetically produced. So elements that do have the same atomic number, like these 3 different versions of hydrogen, but they have a different mass, They are called the isotopes. So the mass of an element really comes from these two. Do electrons add to the mass? Well, yeah, they do. But for the most part, for chemical reactions anyway, we can neglect the electron mass because it's only about 1/2000th of the mass of a neutron and a proton, which are about equal in terms of their mass. For nuclear chemistry, that's a little bit different. Even though the electrons are 1/2000th of the mass, we'll see that that can still be significant in terms of the amount of energy that is generated through nuclear reactions. So yeah, we can have the same elements, the same number of protons, but they can have different masses because of the differing number of neutrons. So I gave you a brief overview with hydrogen, but let's take a closer look at something else. Let's take a look at carbon. So carbon can form three different naturally occurring isotopes. So every single one of these, they do have the same number of protons, and that number is 6. So if you take a look at the periodic table, find carbon on the periodic table, it is atomic number 6, and that means that it has 6 protons. But they can have different masses. They all have to have exactly 6 protons, so that would contribute the same to the mass, but they can differ in terms of their number of neutrons. The number of neutrons can be 6, 7, or 8. And that's what gives us the three different isotopes of the carbon. So we do use some special notation when we're writing about and talking about these different isotopes. So what I'm showing you here, the X first of all, is simply the element symbol. So that would be hydrogen, capital H for hydrogen, capital C for carbon, and so on. The number at the lower left-hand side, let's take a look at that. So Z. Z is the atomic number. It's always going to be an even number, and that's the number of protons. The number of protons. So for carbon, again, that's going to be a 6. It's always going to be a 6 for carbon. It's always going to be a 1 for nitrogen. At the upper left-hand side, the capital A that I have here, that is the mass number, which is not the same as the atomic mass. So the atomic mass for carbon, again, if you take a look at the periodic table, is 12.01 grams per mole. If you have 1 mole of carbon, it weighs 12.01 grams. But of that carbon that's naturally occurring, it's made up actually of a combination of these different versions. The most common version is this one here. So this number, 12.01, is actually an average mass for all of the naturally occurring carbon. But when we talk about the isotopes, we're only talking about one version of the carbon. So for each versions, there is a specific number of neutrons. So here, we're not going to have a decimal for our mass number. It's going to be a whole number as well. It is just the number of protons plus the number of neutrons. So what we can have for carbon is 6 plus 6, 12 for the mass number. We can have 6 plus 7 neutrons, 13 for the mass number, or 6 protons plus 8 neutrons, 14 for the mass number. So this is the way we would show it for the carbon. Again, this is the most common naturally occurring one, and that's why the average is much, much closer to 12 than to 13 or 14. The other two are actually fairly rare. So capital C for the symbol. At the lower left-hand side, again, this is the number of protons. This one at the top here is the protons plus the neutrons. So that's the 6, and it must be another 6 because we have 12. This is also carbon, 6 protons, but now we have 14. So how many neutrons are there? The neutrons will then equal 14 minus the number of protons, and that will give us the number of neutrons, which is equal to 8. Okay, this is the neutrons. This is the protons, and this one here is the mass number. So quickly, just the other version can be the carbon, 6 for the atomic number, and 13 for the mass number. These are the 3 different isotopes for the carbon. I'm just going to exit out of here for a minute and go to the data booklet, show you a couple of things in the data booklet here. So in your data booklet, this page that I'm showing you here is the one for the nuclear chemistry. So this is page 8 in your data booklet. A bunch of information on here that we will be referring to. So these particles, alpha, beta, gamma, radiation, I'll talk about those shortly. Down in the table here, we have certainly not all of the different radioactive isotopes, but a selection of them. And I just wanted to point out here the hydrogen and how it shows 3 different versions of hydrogen. So hydrogen 1, this is the way that it's written. So hydrogen 1 has what? It has 1 proton and it has 0 neutrons. And that's why the mass number is 1 as well. So this is called hydrogen 1. And that 1, the dash 1 after the hydrogen, that 1 is for the mass number, the number at the upper left-hand side. Hydrogen 2, now we have 2 at the upper left-hand side. There has to be 1 proton, which means there must be 1 neutron as well. This is also called deuterium. And that's going to be kind of important when we talk about our Canadian CANDU reactor. And the last one here is hydrogen 3. Again, the 3 is the mass number. It goes at the upper left-hand side. Still a 1 for our atomic number. And this one is also called tritium. So 3 different isotopes that we have here, all isotopes of hydrogen. They're all hydrogen, but they're different versions of the hydrogen, different isotopes of the hydrogen. So nuclear fusion is what does take place in our sun and other stars as well. Nuclear fission is what we do with our nuclear reactors that we use to produce electrical energy. So that CANDU reactor that I mentioned a couple of times, it undergoes nuclear fission in order to, well, eventually generate electrical energy. So most of the elements, they're fairly stable in terms of their numbers of protons and neutrons. They remain that way, but there are some elements, some isotopes that are unstable, and quite often that's because they have a different number of protons and neutrons. They're not equal. And this, we then say that they are radioactive. And what that means if they're radioactive is they're unstable and they're going to decay or fall apart or transmutate over time, and they're going to form some different elements. And in this case, they're going to do that by splitting apart. And that is what fission does mean, is the splitting apart of a larger element into lighter ones. So in the case of this one here, uranium-238, this one here could be transformed into 2 lighter elements. The one that's typically more radioactive is the version that is the 235 rather than the 238, but big huge element can split into smaller ones, and when it does so, that is a fission reaction, and it also ends up generating and releasing huge amounts of energy to go along with it. For Science 30, there are 3 different specific kinds of radiation that you do need to know about. So the first one is called alpha radiation. This is the symbol here for alpha. This is all once again in your data booklet. So what an alpha particle really is, it's a particle that has 2 protons, which automatically makes it helium. It also has 2 neutrons. So we would then add those together to get a mass number of 4. And this is going to be produced or emitted, and that's why it's called alpha radiation. So typically, you will have a larger element that's being split apart, a fission reaction, and one of the products that is produced is going to be the alpha particle that we see right here. So again, this number 2 is the number of protons. The number 4 is the mass number. That is the protons plus the neutrons added together. So I'm using the term radiation, that is what it's called. In fact, these ones have very, very low radiation. You could block these alpha particles with a piece of paper. Very quickly, they pick up electrons as well, and then they just turn into a regular run-of-the-mill helium. So this is a couple of examples of this sort of radiation that we do have here. So this is uranium-238. So in this case, it does actually decay and form our alpha particle. Okay, so this is our alpha particle. You should recognize that as the alpha particle. And the other one that it's forming is thorium. You don't need to remember the names or any of these symbols. It's all on your periodic table. And most of these are also in that table that I just showed you as well. So here we have uranium that is being split apart into two completely different elements. So that's why it is a nuclear reaction. Big going into small, that's what makes it a fission reaction. And the fact that the alpha particle is produced is what makes it alpha radiation. I'll just make a little note here about balancing of nuclear reactions. Eventually you will have to balance these as well. It's pretty straightforward. The number that you have for the atomic number on the reactant side has to equal what you have for the numbers on the product side. So quite simply, 90 plus 2 has to equal what we have, what we started with 92, otherwise something is wrong. Same thing with the mass number, 238. That number has to be equal to what we have on the product side, and it is. 234 plus 4 is 238. So the next one that I have here, this is polonium-210, 84. For the atomic number. I believe this is protactinium. Oh, sorry, that one is lead, not protactinium, lead that we do have. Lead 206. And again, the key here is that we have our alpha particle that is forming. So this again is alpha radiation. It's a nuclear reaction, yes. It is a fission reaction, yes, because once again, we have something big that's being split into things that are smaller. And then it's also, of course, the alpha radiation. So what are some other kinds of radiation that you need to know about? Well, this one here, beta radiation. So what is beta? Well, it's really just an electron. So E for the electron. This is 0. It's not saying that the electron has 0 mass, but there are 0 neutrons and protons. Add those together and that does equal 0. Down here for the number of protons, well, there are no protons, but what we do have is -1 for this beta particle for the electron. And just a point here that these electrons, they're not coming from those ones that are in the electron orbitals, but rather they are originating from the nucleus itself. So beta radiation, what does it look like for a couple of reactions here? So in general, I just have a neutron being split apart into our proton and the electron. So that could be this is our beta that we do have here, our beta radiation. A little bit more specific, showing the neutron. It does have a mass number of 1, no protons, so 0. And what is being formed is our beta particles. So again, you do need to be able to identify this and realize that yes, this is beta radiation because that is what is being produced. What else do we get? Well, this is our, well, it has here hydrogen, but it really is this one here. It is a proton. So hydrogen without an electron. This is the electron that it just lost. That's going to be a proton, and it doesn't have a neutron either. So the atomic mass, of course, is 1 because it is hydrogen, and the mass number is also 1. And the one at the bottom here, thorium, this one here is our protactinium, and again our beta particle. Balancing once again, all we need to do, these numbers here, 234 plus 0, have to add up to the mass number that we have on the reactant side, and same with these ones, atomic number. So 91 minus 1 equals 90. That has to add up as well in order to balance nuclear reactions, but we'll be getting into all of that and another lesson for nuclear calculations. The final kind that you need to know about according to the program of studies is this one here, gamma radiation. This is the symbol here for gamma. So remember, gamma rays are, if you think back to electromagnetic radiation, they are high energy, very, very high energy, ionizing radiation damaging to biological organisms. This emission, again, is coming from the nucleus, and it's when the nucleus is going from an excited to a lower state. And you might also get the alpha and the beta particles that are being produced. But in this case, we do get a massless particle, energy but no mass, and that is our beta particle. So finally, I'll just show you these three different, and then one other one it has at the bottom here, and then I'll go back to the data booklet for a minute. So alpha decay, you should be able to take a look at any of these and identify which one is which, simply by taking a look at what you get. This here is the alpha particle, it's alpha decay. This is the beta particle, it's beta decay. This is the gamma particle, and it is gamma decay. They do also have this one in your data booklet, a positron. So I suppose you could maybe get this one as well. But in terms of the program of studies, these are the big ones that you do at least need to be able to recognize. So to finish this off, I'm just going to go back to the data booklet and just show you where you can find all of this information in terms of the radiation. So no, you don't need to remember what an alpha particle is, because under this first table here, subatomic particles or radiation, it tells us an alpha particle is simply the helium. It's the helium nucleus with 2 protons and 2 neutrons. It even gives us the symbol for it. We'll talk about this later, but it gives us the mass of that alpha particle. Beta, again, it tells us exactly what it is. An electron gives us the symbol for it. No memorization required at all. Gamma radiation, this one here, we have the symbol for it. 0 for both the atomic number and the mass number, because, well, it does have no mass. And as I mentioned, it does also have the positron in here as well. Positron is essentially the same as an electron, a beta particle, same mass, only one has a positive charge, positron has a positive charge, and the beta particle or the electron has a negative charge. And yes, a beta particle is just an electron. They are one in the same thing. And finally, on this first table, it does have the neutron. Neutron, 0 protons, but 1 for the mass number. And for a proton, 1 for the number of protons, 0 neutrons, so also 1 for the mass number.